Okay, I said I'd make a video about the filling the tank problem. So, here's the problem. Let's take a minute to maybe pause the video and look at what's important. So, let's see. Well, here we see that water is being pumped into the tank at a constant rate of 2 cubic meters per minute. So, that means that the volume is changing at a rate of 2 cubic meters per minute. And what do we want? Well, it says find the rate that the water level is rising when the water is 3 meters deep. So we want, well, what do we want? We want the rate that the water is rising. Rising sounds like the height is increasing, so I guess we want to know how this height is changing when the water is 3 meters deep. So when the height is 3 meters. Okay. And the other problems in here, we have the radius 2 and the height 4. Those are how we drew this picture down here. So we have a relation that v equals 1/3 pi r squared h. That's the equation for the volume of, let me fill in this, actually let me make it blue so it represents water. So this is a formula for the volume of this shaded region. And we could proceed in a couple different ways, and I want to do both of them here. So the main thing we have to think about is that we have, at this moment, we have r and we have h, right? And so if we're going to apply the derivative, we're going to take d dt of both sides. Well, we can expect, obviously there's a v, there's an r, and there's an h. If we look at what we know, well, we know dv dt, that's up here. And we want to know dh dt, right? That's also something we know, or something we want, but we don't have any information about dr dt. So that's going to be maybe a problem. And so I think what we're going to want to do is first get r in terms of h. Right? So if we can rewrite our problem so that r is in terms of h, then we'll be able to take the derivative and we'll only involve dh dt, which is what we want. And so how do we do this? Well, this is where a little geometry can help. We have these two triangles. Let me draw them down here. One is a 2x4 triangle, and one is a r by h triangle. Right? And if you remember from geometry class, these are what are called similar triangles, because the 3 angles in those triangles are the same. And what should be true of similar triangles is that if we do ratios of corresponding sides, like for instance 4/2, so that's the long leg over the short leg, we should get the same answer as doing h/r. Right, so this long leg over the short leg should be the same as the long leg over the short leg. And if you want another reason for that, you can think about this angle down here. The tangent of this angle should be 2/4 from the big triangle, and it should also be r/h from the small angle, from the smaller triangle. So in either case, we should get the same answer. So in any case, we have an equation now, and so we can solve this for r. So if we solve that for r, we're going to get r equals 2h/4, which is h/2. So let's sub that into our relation. V equals 1/3 pi h/2 squared times h. And when we simplify that, it's going to be pi h squared over 4 times h, and we get pi over 12 times h cubed. Okay? So that's our formula. So actually let's copy that and let's transfer that to our next page. And now let's apply d dt to both sides. So we take d dt of v, that should be the same as d dt of the right hand side. That's dv dt equals 3 pi h squared over 12, we use the power rule, times dh dt. Here we're using the chain rule. And if we simplify, that's going to be dv dt equals pi h squared over 4 times dh dt. So if we go back and we look at what we knew, well, luckily we filled this in. Our given was dv dt was 2. We wanted dh dt, and h was 3. So if we plug in, we're going to get 2 equals pi times 3 meters squared. Maybe I'll put units over here. And that was per minute. Over 4 times dh dt. So when I solve for dh dt, I get that dh dt is going to be 8 over 9 pi, and then I get meters per minute. Okay? And that will be my answer. So this is how we can solve related rates problems by setting up the problem. If we look back, we wrote down what was given, and we substituted that in to solve our problem. So thank you for watching. Have a good day. Bye.